Okay, Charlotte, go ahead.
Okay, so welcome back everyone to the last day of the Wavefront Sensing Workshop. So plenty of very interesting talks to come up. Just a couple of quick reminders. We have the Discord channels for discussion. And please direct your questions to the Q&A panel through Zoom. So let's get started. And so happy to introduce our invited talk from Maud Langlois on extreme adaptive optics wavefront sensing with Mach-Zehnder. So please take it away, Maud.
All right, thank you very much. Thanks for the invitation. I'd be glad to present the work we've done for a few years on the Mach-Zehnder wavefront sensing for high contrast imaging, and this has been done thanks to many people. Few are listed there, and mainly the new development have been supported by my PhD student Camille Graff. Okay, sorry. So basically, to remind you with the extreme AO challenges and high contrast issue is that you want to maximize trail. Everybody probably is aware of that, and just the aim is to concentrate most of the energy in the diffraction peak and have a minimum halo residual surrounding this peak. So also minimizing the static aberration, quasi-static aberration, to also remove speckle effect that limit the contrast. So this is a big challenge because then it obviously requires many degrees of freedom to reach this kind of contrast, and also minimizing all the source of errors. Previous study have already compared different wavefront sensing technique, and we have heard a lot of Shakartman wavefront sensing and pyramid, which are the way to go now. Alternatively, on a sensitivity basis, the Mach-Zehnder offer some interesting characteristics, which previously were kind of difficult to deal with because of the small dynamical range. So other advantages also of the Mach-Zehnder compared with the other technique is that really it's a sparse system, and I will try to illustrate this, and I will also show you how we can actually deal with such wavefront sensing when we actually want a real AO system without a first stage correction, for instance. Also, yeah, this is a old paper from Olivier Guyon comparing then the level. So I've talked about Strel ratio, which is directly related to the amount of energy that is not in the peak and that is sitting surrounding the peak of the image. But then in terms of contrast, if we compare the pyramid, which are the black line, no modulation, which is the dash line, and the modulated version, as function of the separation, you see that you want to have no modulation to improve the accuracy of the wavefront sensing, and then remove most of the halo and reach the higher contrast. Compared to that, the Mach-Zehnder wavefront sensor is a similar pattern in noise level and accuracy to the non-modulated pyramid, and it is shown in green. So on the principle, so the Mach-Zehnder wavefront sensor is an interferometer-based wavefront sensing. It has actually two arms which are separated, reflected on different part of the device. One arm is the phase measurement arm, and the other one is creating a self-reference phase, which act as a reference to measure the fringe. Well, so the fringe interfere and measure the wavefront if you have a perfect reference. And this is created by a pinhole reflection, which has a diameter close to a lambda OD. Basically, then in your fringes, you encode the phase independently on each pixel of your pupil. So if you image your pupil, and that we see on your upper right, you have an image, a raw image of the Mach-Zehnder, where it has aberration, and then we also introduce steps with using a special light modulator. So you're transferring your phase information into an intensity, and it's not such so simple problem, because you know that they are encoded on a sine value. So you have basically the intensity you are measuring directly on your camera is a factor of intensity, a constant, plus a factor, a multiplicative factor, times the sign of the wavefront you want to measure. So simple way to extract the signal is to do the normalization and the subtraction of the two outputs of the wavefront of the Mach-Zehnder. Similarly to the pyramid, you just do I1 minus I2 and divide it by the sum of the two, which are the two outputs of the Mach-Zehnder, and then you get some signal which is proportional to the sign of the wavefront you want to measure. In fact, this works, but then if you want to be really quantitative, so in closed loop, you can probably handle less, but to be really quantitative, you want to really separate the intensity part from the phase part, and to do so, you need to calibrate all the terms, all the constant terms, which are the A0 and B in the equation above, to really retrieve both the intensity distribution in the pupil and the phase separately. So we can do that by introducing a program diversity. So basically you fit a sign response knowing that you've included some phase aberration of given steps, and you need roughly between 3 and 5, and you can then get independent intensity pattern and phase estimation. This is an example of these two outputs, the A0, so the constant term in intensity, so it's basically intensity repartition in the pupil on the left, and on the right, this is the phase that is associated with the measurement at the time it was done. It's not in closed loop, so there is some phase shape, which is normal. Basically, in simulation, you can simulate all this. It's not very complicated. It's just a Fourier filtering from the pinhole to create the reference against which you measure your fringes. And then you have a simple reconstruction. Numerically, it's easy to do just to assume that the coefficient, the constant are easy to estimate, and you can just use the simple equation. This leads to very high strain, very small phase variance, and so on. So the major issue is then to extend the dynamical range of this measurement, because the sign, then you only measure something which is pi over 2 and between pi over 2 and minus pi over 2, which is small dynamical range. So we can do that by introducing a node modulation, and it could be, for instance, a wafer pattern as shown here. It could be something else. You just need to add information that will enable you to have both the sine and the cosine of the phase, and then you can extend double basically your dynamical range and get in the range when you can use also a more traditional technique to unwrap the phase further. So this is working well in simulation, but also in real life. As I said, we can use waffle, but anything that adds diversity. So you need to find shapes that are not bothering you in your image plane, but it's not so problematic. To increase further, so Camigraph has tested proximity unwrapping method based on the Giglia paper from '94, and you see above on this figure, you see what is the measurement out of the Mach-Zehnder in orange. Then if you use modulation, you get to the green, and then if you do the unwrapping further on, so this unwrapping is using then information between two pixels, as opposite to the Mach-Zehnder measurement, which is just pixel by pixel, you measure independently. Here you relate the pixel, and then you can unwrap to large phase errors, as shown here, which you have almost 20 radiant phase error. How is it built? So it's basically a two-phase plate of equal thickness, some coatings, and the main point is to have a reflected pinhole that acts as a special filtering. There is no moving part, and also you can then, to calibrate, introduce some diversity. You cannot then separate the two legs anymore, so you have to be clever and use your DM to do that. So we have at CREL an EO bench which has been built to scale up to the ELT instrument. And it uses basically several components that we've all seen on the different existing bench, a spatial light modulator with many pixels to either create a turbulence or correct for it, and a deformable mirror, which for us is a Boston micro machine with 12 by 12 actuators. And then also it has several cameras. I mentioned the pupil camera, so looking at the pupil, but we also have tricks to check the alignment on the pinhole and the level of aberration on the pinhole, because it's quite important to get it right at this location. I will not go too deep into the scaling, but basically it's large number of pixels for the wavefront sensing. So now we have a pupil with more than 1,000 of pixels, which then is a lot for a current telescope, but could be more relevant to ELT. We have a deformable mirror with not so many actuators, but very useful to control the NCPA. And then also some turbulence phase screen, which has didn't mention, which are pre-corrected phase screen for representing the ELT first AO loop correction. Now we run quite slow. So our aim, and I will finish with that, we plan to really run faster. And we are already have an RTC to do so. We just need to get it running. And it's not so simple to interface everything and make the full thing operable, but we will get there at some point. So the setup, you've seen the picture. It's basically using either helium neon sources, but also super continuum white light sources and diode laser. Now we plan to extend our capability to the near infrared up to 900 nanometer with a new prototype. What I will show you is basically around 700 nanometer. We will actually get a new camera, C-Blue one, to be able to go on sky at some point, which will interface with the current system. And the rest I told you already. So if you look on the right side and you see I don't see my cursor, but you see basically the solid Mach-Zehnder, integrated Mach-Zehnder, and then the relay camera at the end. It's quite complicated because we tried to both image the pupil and the pinhole together, as I mentioned, to correct for the NCPA at this position. Here is an example of the influence function as recorded by the Mach-Zehnder directly. So you see the two outputs of the Mach-Zehnder. And then when you push one side, the opposite is actually the opposite color. That's totally normal because you get a sign and minus sign on the other pupil, and that allows you to calibrate the intensity as well. So this is just a raw image, background subtracted, and that's it. And you see all the Boston micro machine actuator pushed up simultaneously on both pupils. Then on the bottom, you see the number of the actuator. As usual, we're all using the same tools. On some occasion, it's wrapped, but we have means to unwrap it and fit the PSF, and also inverse the metrics as usual. This is another example. So we actually decided to do calibration a different way recently by generating not as many influence functions, but few well-selected screens. This is an example of a screen that is used. So it's just generated by the DM. And then you see on the left the phase that we introduce on the DM, and on the right, what is measured directly on the Mach-Zehnder. This is just the phase. And if you look closely, so the two circles I highlight, you see that at this position, it is actually wrapped. So we cannot just do the standard inversion of the sign to get the phase. We just need to unwrap. But as I said, modulation helps that, and if you have enough diversity, it works well. Another, maybe an illustration that is quite older, but how does it works exactly? You see on the bottom left, an actuator which is actually pushed, and you see a cut curve, you see that it's wrapped. And then by using the modulation as illustrated on the right, you actually see that it's actually able to unwrap this actuator, for instance, illustrated here, which is the only one used. So just to demonstrate that the modulation works in lab and in simulation, also in the lab, we can generate what we want with the SLM, and we tested the accuracy of these measurements, and it can really be below a few nanometers precision. We actually see the gray steps of the SLM, which is a good sign, even though it doesn't exactly work the way we want it to work, but we see a few things with it. This is an example of a diluted pupil. So we can do the exercise by having really a small pupil in your big pupil, and we can mask the intensity. Here we just add phase on several circles, and you see the phase that is introduced on the SLM is on the top at the middle. I will run both movies. So the movie on the left is basically the same thing. So it's a global phase on the bench on the left, corrected on the right. In addition to this, we add the phase value that is on top of on the image. And as you see, it's supposed to be a fixed phase value, but the SLM is actually oscillating as if it basically just keeping oscillating and not settling in a final position, which is something we are trying to sort, but at least it also shows that we can measure big phase steps which are not linked together, which other wavefront sensors have trouble with, and we are confident that we can basically phase and measure the turbulence on such a telescope configuration. It could be larger, it could be also island effect. We are an absolute phase measurement in any case. The only drawback is if your step in piston is larger than a wave, you will have to do multicolor, because then there is still the ambiguity as usual. But that's the only for the final ambiguity, I mentioned Giglia, and there is also a drawback is you need to have less than pi phase difference between 2 pixels, but which basically never happen with the structure function of the turbulence, so you are safe from that side. It's just this case with a large piston, and then you have to maybe find a solution with using multi-wavelengths. We also did simulation for such a pupil just to test, and you see the introduced phase, which is turbulent, no piston error here, and just a recovery. It's very high strain on all the sequence. We've tried temporal evolution as well. Maybe the last part of my presentation, I will show you results, because we use the wavefront sensor on sky and at the William Herschel telescope, using the Canary adaptive optic system as a first correction, let's say. So you probably all know this system. It was a short time experiment, but we really want to get there. And basically what we did is measure after the AO correction the phase. Integration, so we needed to change a little bit, actually, if we go, you look at the picture on the bottom left, this is the CRAL AO bench, and then we needed to make it much shorter, and also we needed to reduce the size of the pupil by a factor 10, so it actually makes the system very, very small. So William Herschel is on La Palma. It's quite good condition there. We had to interface with the telescope in a very small space. So you see some of the interface. So we come after the AO system and on an optical bench. We also had in parallel another wavefront sensor, which is CAOS, which was developed by the Durham team. And we plan to measure simultaneously the same wavefront error. So this is basically the bench before we went there, and this is where we went. So you see in orange, basically the Mach-Zehnder path with the very small, tiny, and lots of optics in tiny space just before the camera. And in parallel, we had a PSF viewer, so like a science camera. The first step is pointing your beam, converging beam to the pinhole to get the light to reflect out of the pinhole to make your reference. So you need to find that pinhole. So on extended, seeing limited beam, it's quite easy. So you see it in a yellow arrow here, and then once you find it, you can close the loop and get your measurement done. This is an example.
Just a couple of minutes left, Maud.
Okay, I won't be too long. Just some result. Then one point is, as I said, you need to focus your beam, and your beam needs to be fairly good. You need to get enough energy reflecting on it. So you need also to correct the NCPA to perform this. So we did that by using an algorithm developed by Michel Talon for the TEMIS adaptive optics system, which is based on maximizing the variance on the PSF image, but also we did it on the pinhole. So on the science camera, you see before the NCPA correction and then after on the right. And we can also do it directly on the pinhole by viewing the pinhole, and which is very useful for the Mach-Zehnder front measurement. So the signal, I will pass rapidly because I have few movies to show you. Same thing on the right, on the sorry, on the left, it's the science camera image. On the right, it's actually the measure signal, which is the raw signal from the Mach-Zehnder. And here we are just replaying the command that were used to correct the turbulence on an internal source. And as you see, there is the actuator very near the center of the pupil are not very well constrained because they are underneath the obscuration when you are not in the calibration mode. Same here, you see this is then real turbulence on sky. We, as I mentioned, had modulation. So we had the Wavefront pattern, which you can see very well on the image plane. And also you have the measurement on the right using the Mach-Zehnder, with the full telescope. This is a fully reconstructed, unwrapped signal of a small sequence of the turbulence measurement after the canary correction. And then I will maybe highlight. I have just few slides. So the Wavefront pattern is not so disturbing for high contrast. It's actually useful addition generally. And here I just show a measurement with different level of Wavefront pattern. You can see them in the science plane if they are bright enough, and barely see them otherwise. But we recover them in the Wavefront measurement by the Mach-Zehnder. One step further is we would like to combine Mach-Zehnder wavefront sensing with some coronographic capability, which is not very difficult because we already have a reflected mask which could act as a mask. We could add the 4-quadrant and deliver together wavefront sensing and coronography as outputs. Conclusion. So we actually proved that we can reach high accuracy even on faint stars. So there will be a detailed simulation on this by Camille soon. The alignment and the stability is simple compared to the old version of the Mach-Zehnder with separate harm, turbulence in between, and so on. Now it's integrated and it's very stable. It's the only way to measure phase and amplitude, which could be used to measure scintillation, for instance. And then also we can correct piston on even diluted aperture or in presence of island effects. It's really a pixel-to-pixel response. I show you maps with intensity and phase in the pupil. This is just done in parallel for each pixel, and except if you want to unwrap, you don't have to break the sparsity. So the dynamical range is actually suitable for turbulence, and you can envision a single step as long as you have proper tip tilt, because you need to have enough photons hitting that pinhole. So the next step will want to close the loop at higher speed, even higher than 1 kilohertz if we can, use iterative and inverse approach methods, auto-calibrate, so we don't have to do the modulation, we can be more clever than this. And we aim at closing the loop on sky with some tip tilt servo correction. And in parallel, there is a development with the same wavefront sensing for metrology, because it reaches very high performances. And this is the work performed with the LMA in. Thank you very much. Sorry, I was a bit longer. If you have any question, I'd be happy to answer them.
So there's a few questions. We'll maybe just take one or two now, and people can discuss on Discord further. So we had a couple of questions on does the Mach-Zehnder and the unwrapping in particular work in the case of a pupil segmented by spiders?
Yes, indeed. So what I showed is a given configuration. We can actually block the intensity and only use the pupil. It doesn't change anything. So we are really an absolute measurement between different pixels anywhere. And if they're not related by any intensity, it's fine. So it can handle any configuration.
Right. A question from Anthony Berdo. Using a pinhole for the interference means that a huge part of the light outside the pinhole is lost. So what is the efficiency compared to, say, a pyramid in terms of the incoming photons?
So we're using really the center, which has still a good amount of energy, and the aim is to use the rest to do some coronagraphy directly. So there is no loss, actually.
Okay. Well, thank you very much. And yeah, I think a couple of other questions you can maybe answer on the Discord chat.
Yes, indeed. Okay.
Thanks.
Thanks very much.
Okay, so next we have Sylvain Auberti. Maybe Maud, if you can stop sharing your screen.
Yeah, I'm still fighting with my cursor, so it doesn't seem. See here. Okay.
Okay.
Thank you.
Yeah.
Sylvain?
Yes. You hear me?
Yes, we hear you. We see your screen.
You see my screen or my slide? Let me see once again. Do you see the main slide?
Yes. We do see your notes on the side.
Okay, that's not good then. Or did I do that before?
Go to display setting on the top left.
Display settings.
Yeah, this one.
Is that one?
Yeah.
Yeah.
Correct.
There we go.
Thanks. So thanks a lot for organizing this very interesting workshop. I'm sorry not to have time to see you face to face in the evening, especially, but maybe next year. So I'm Sylvain Auberti. I'm glad to present here some results on the GALACSI NFM mode, which is the VLT's laser tomography AO mode. I was in charge of its commissioning, and more recently, I acted as a project manager for the YOLOS upgrade project, and I'm speaking on behalf of the full AOF, GALACSI, and YOLOS upgrade teams. Yeah. Okay, so Muse NFM mode is an amazing science machine. It's producing lots of science since 2018 with NFM mode. Last week, there was a published paper describing the recent detection of a pair of supermassive black holes very close to each other with NFM mode. You know, in the past that Muse NFM mode has been used to discover protoplanets with their H-alpha emissions. and it's doing lots of exciting science. This is another example of type of sense we can do. This is a globular cluster seen by the HST in the visible. On the right side, you see the similar field as seen by Muse in wide field mode, with the GLAO system offering an n-squared energy doubling in 0.2 arcsecond pixel size. With narrow field mode, this is what we get. So a much higher spatial resolution, basically 10 times higher spatial resolution than in wide field mode, with trail ratio above 5% at 650 nanometer, supposedly in good seeing conditions, but not so bad when the seeing degrades. The combination of the spatial resolution and spectral resolution of Muse in the visible is really outstanding, but there were some improvements to provide. First, to improve the tomography that we delivered in 2018, and secondly, to improve the sky coverage and the tilted residuals on the bright end, because we were limited so far, until this year, to J magnitude 15th as the faintest end. So this is a short timeline of the project. It was commissioned early 2018. We started the ear loss upgrade project to improve the limiting magnitude in 2019. At the end of the same year, we improved the tomography by essentially solving the reconstruction of the lower order modes and then pushing the regularization to drive more high order modes. This year, we have commissioned the ear loss upgrade in 2 runs. First in March, AIV and commissioning 1, and this summer, the commissioning 2, which is the final one. Last week, we had a technical time to explore the tomography parameter space, where we could do a short super resolution demo. And that was not my plan initially, but since it's a hot topic of this workshop, I will spend some time on this. So ear loss is the low order wavefront sensor for Muse. It provides fast tilt correction and true sensing for defocus and astigmatism, plus the capability to observe extended targets. The upgrade consisted in removing the old Huawei detector with 11 electron without noise, and to replace it with the Zafira technology, which is the same baseline as for Mavis, Harmony, and Maori, doing tomography with lasers. This is a technology developed by Gerd Finger at ISO and Leonardo, and it has sub-electron without noise. We expected to gain about 2 magnitudes and wanted to make a fast project in 2 years. But COVID arrived, and we had to do the MAIT in 2020 during COVID times. We went through, and we could do our first remote AIV and commissioning in March this year. So nobody from the design team, the core team, traveled from Europe to Chile. The full commissioning was handled by our Chilean colleagues. Here, Pierre Bourget performing the integration of the cryostats at the NASPIS platform. We performed some remote training, and many people were connected during the night from different places to perform the commissioning. That ran quite smoothly, but with great support from the Chilean staff. Commissioning 2 was dedicated to the faint end mode deployment after we had delivered the workhorse mode in the bright end. This is a short illustration of the total noise we get on sky in a bad case where we have clouds with quite high sky background. This is a kind of a worst case scenario where we have 1.2 electron RMS. Normally we get about 0.8 electron RMS per when we run at 500 Hertz on a large pixel scale of 78 mass. Under these conditions, we tested the faint end with a 2x2 mode at 200 Hertz, and we had pretty good seeing conditions, but yeah, cloudy skies. And we could reach, we could close the loop robustly until magnitude 19.3. Acquisition was a piece of cake until magnitude 19.5 and possibly fainter. It's interesting to note that at this magnitude, we had 2.1 photon per frame per subaperture, which with the noise conditions we had at 200 Hertz is equivalent to an SNR of 1. And I think that we were close to reaching what Olivier Guillon mentioned yesterday, to the fundamental limit with 1 photon per frame with a 1 radian square error. Here, actually, we have alpha radian square error. This is a showcase that we did in the second run. So we observed the Einstein cross, which is an object of interest that was part of the initial science verification of Muse narrow field mode, but that we miserably failed to observe, as the instrument scientist puts it. because it was too faint. Now we can guide on this image of the quasar at magnitude 16 in J, and it's straightforward. It's actually a bright object for GALACSI narrow field mode now after the loss upgrade. And we can see that even in bad seeing conditions, we get a very high spatial resolution image, bearing in mind that each pixel is actually a spectrum compared to the HST. And you can see the correction radius on this short exposure, whose size is 0.4 hexagon radius, which is consistent with controlling 850 modes. So really nice observation with the science announcement together with it. And as a conclusion slide, I would like to say that the so GALACSI narrow field mode is the only LTO system in operation. It delivers high performance and robust science for the last 4 years, and it's going to be even greater now that scientists can observe fainter targets. The performances are good, especially at the AO focal plane, a bit degraded on the news images. We still need to work on some static aberrations. After the upgrade, we go 4 magnitude fainter, while our goal was 2, so good. Before the upgrade, we could offer magnitude 7 to 15. Now it's 0.5 to 19. We also improved on the bright side, actually. And we have also improved the off-axis guiding capabilities to increase sky coverage to some percent, possibly 9% of sky coverage in the best geometric case. And we have, by pushing the tomography, controlling more modes, and going faster with the TT correction, we are now less sensitive to tau knots and seeing, which allows to operate this mode under various conditions. So to finish, I would like to talk about super resolution. It has been introduced already in this workshop by Carlos, Thierry, and Jeff. I just would like to highlight one aspect that's important to me, is that when you apply a fractional shift of several sampling grids, you generate somehow a meta sampling grid. And if you go to the Fourier space, you find the typical terms of the sensitivity functions, which depends only on the subaperture size, so it's unchanged, while the direct comp has a period that has changed. What it means, in short, in a nutshell, is that for multi-wavefront stereo systems, we can decouple in our design the size of the measurement cell from the sampling period. And this is new, and this is a game changer that we can use in optimizing our designs. Sorry, I didn't say, there is a concept paper to be submitted as soon as possible. Now, a few results of last week's short experiments. We had 2 hours on Sky, a couple of hours, I should say, to test proof of concept of super resolution on Sky. So what I did is take my 40 by 40 slopes of all the 4 wavefront sensors and bin them in 20 by 20 or 10 by 10 with transformation matrices that were plugged into the control matrix for the NVM, basically, so fully transparent for the real-time control. It's important to know that GALACSI narrow field mode is based on the pseudo-synthetic model approach, taking into account the misregistration in the model. So the misregistration between the DM image and each wavefront sensor channel in terms of shifts, rotation, and stretch, as seen by each wavefront sensor. And as you can see, they are different from one wavefront sensor to another, and they vary with elevation, with the flexures of the telescope, and also the flexures of GALACSI that is sitting in the adapter rotator at NASMIS. There was a question on the first day, is there any instrument using super resolution? The answer is yes, we do. We take that into account in our model, and actually we will construct more modes than we can control. So in the tomography, we will construct 1,300 modes for each layer. Then, once this tomographic reconstruction is done, we project the phase on the degrees of freedom that we can control, and we filter the KL modes that we want to keep as a trade-off between performance and robustness. These are the singular values of the matrices I generated for this test on Sky, with 10 by 10 in blue, 20 by 20 in pink, and 40 by 40 in red, either centered in dash or shifted with the real system shift in a solid line. And here you can see the model interaction matrix from the ground layer, and here from an altitude layer at 10 kilometers. And what you can tell is already in the pupil plane, by shifting, you get the expected advantage from super resolution in 10 by 10 and 20 by 20 quite significantly in pushing basically the sensitivity to larger degrees of freedom. For the native resolution of 40 by 40, you see mostly a gain here on the least seen modes, where you have a higher sensitivity to these modes. So this is where you can benefit for an aliasing reduction, for example. And on the altitude side, you see that shifting or not doesn't make a difference. And that just confirms that the super resolution is built in the altitude layers, obviously, because the shift is there by design. Some results on sky by applying this 20 by 20 so bin control matrices in red compared to the baseline LTO 40 by 40 in blue. So in H-band, we couldn't see difference in trail on sky. The PSFs were very similar. We went to the visible to witness there a significant difference of performance, which we can confirm by looking at the residual PSDs. So on the top here, you see the residual wavefront error as seen by the wavefront sensors, so off-axis. And at the bottom, the projected wavefront error on axis, so reconstructed on axis wavefront error, where you see that the classical LTO, so sorry, the color code is inverted. Classical LTO is in red, and the 20 by 20 is in blue. So you can correct it to 850 modes. With the 20 by 20, we correct up to 600, and then we have basically the same variance as the atmosphere. This is based on the R0 predicted by the RTC, the black line. It's interesting to have in mind that also in the super resolution 20 by 20 case, we drive here the 850 modes of the DM. So even though they are poorly compensated, they don't lead to divergence or strong degradation of the performance. Actually, by looking more closely, what I figured is that I was not aggressive enough on the regularization. Basically, we had such a short time, so I wanted to close the loop, and I put a lot of weight on the noise, so giving less confidence to my measurement. The result is to have low modal gains on the high order modes. So all these modes, around 600 and more, are controlled with a very low modal gain. And to confirm that, we did the last test where on the sky in closed loop, we applied push and pull of Karinen level modes, so number 100, 200, 300, 400 until 800. And this was done while closing the loop with the 20 by 20 shifted control matrix. And we can see in each of the push and pull a damping of the mode whose amplitude is reducing with the spatial frequency, basically. So we have a rejection at each spatial frequency, even at 800, but we can see that the modal gains are decreasing, and this is actually consistent with the modal gain that you can see in the tomographic control matrix. So the next step is to work on more aggressive regularization and to go on with such tests, possibly mid of December, where we have a bit of technical time again. I hope that I was in time, but I'm done. Thank you.
Thanks, Sylvain. Very, very interesting. I don't know if we have time for many questions, but I just had a quick one. When you do the 40 by, when you use the full resolution, do you reconstruct more modes than you can control with the DM?
Yes, so but not so much more. So 1,300, while we can control maximum 1,156. I mean, this is the total number of actuators. I should gain by reconstructing even more modes than that, but it was a choice of computational efficiency, basically, not to put too many modes in the computation.
Okay. Thanks. So thanks a lot for that very interesting talk. So next we have Hao Zhang. Oh, sorry, for some reason I can't share my video, but I'm waving at you. Do you want to go ahead and share your slides?
Yeah, sure. If you can hear me.
Yes. We can hear you. We can see your slides.
Yeah, I'll just, sorry. Okay, so can I start now?
Yes, go ahead.
Yeah, okay, thank you. So good morning, afternoon, evening, night. So my name is Hao Zhang, and welcome to my presentation. So I'm currently a last year PhD student at the Australian National University, and I'm under the supervision of Francois and Damien. So together we are working on the field of AO simulations, AO tomography, and control schemes. And today I will be introducing our recent progress in this field, global tomography for MCAO systems. So as you may know, we work on this MAVIS project, and MAVIS is basically a visible band MCAO system that is currently in this preliminary design phase, and it will be eventually equipped onto the UT4 of VLT in Chile, and we hope this to be in 2027. So we do have a lot of exciting science cases and other interesting stories about MAVIS. So you may refer to this second and third paper for more details. So in this presentation, we focus on this system configuration. So basically, we hire 8 laser guide stars, and this is using the 4 laser guide star facility and splitting each laser beam into 2 separate guide stars. Therefore, we have 8 in total. And we also have 3 natural guide stars for this low order and truth sensing purposes. So after that, we use 3D deformable mirrors to perform this 3-dimensional composition, and we can have a larger field of view that is a 30 arcsecond sans field of view square. And the overall STREL ratio goal for MAVIS is quite challenging. So it's no less than 15% averaged over the whole field of view, and this is down to the V band and on the median seeing conditions. So we do have a lot of challenges, and personally, I have been working on this control algorithm to improve the overall performance. So basically, I'm working on this learn and apply algorithm, and as you may know, this is first generated by Fabrice in 2010 for MOAO systems, and this is extended to MCAO applications a couple of years later, and it has shown very good performance for the MAVIS project. This is basically from the simulation results. And it takes 2 steps. So the first one is a learning step that is basically identifying the atmosphere turbulence profile. And this is typically not real time. So basically using the recent telemetry buffer and take an iterative least squares optimization process. And we can update, we can have an idea of the CN square or maybe altitude and the other parameters that we are interested in. After that, we have this apply step, which is more related to this talk here. So this is a tomography method, tomographic reconstruction, and more related to the real-time control. So basically optimizing the deformable mirror command vectors. So basically we have 20,000 measurements coming from the wavefront sensor every millisecond period, and we have to optimize for approximately 5,000 deformable mirror actuator commands. So regarding the basic theory of the learn and apply scheme, we do have this assumption of the virtual guide star. So this is my naming, and maybe you have a better naming for this. So basically, it's very close to the conventional MMC method. And the difference is that the MMC is generally working from a phase space, but we are actually focusing on this slope space. So we define these virtual guide stars that are fictive guide stars that never exist. But if they do exist, we can make a very easy control scheme from the measurement from these virtual guide star directions. So there are basically a couple of high order natural guide stars that is distributed over the field of view, and we can tune the actual MCAO performance by tuning the constellation or the numbers of the virtual guide stars. So this is basically saying the problem is to optimize the residual slope on the directions of the virtual guide stars from the real measurements, and this requires the use of a slope space covariance matrix between the wavefront slopes measured by the actual wavefront sensors and possibly by the virtual guide stars. So recently, we have been working to promote this algorithm by introducing a predictive step in the scheme. And this is achieved by using this von Karman turbulence model and this frozen flow assumption. So based on all these assumptions, we can introduce a time shift in the covariance matrix. And in the learn step, we can also identify the wind speed, wind direction for all the atmosphere turbulence layers. And after that, we can use this information in the tomographic reconstruction to mitigate the impact of the servo lag. So we do address this limitation here. So previously, all the predictive reconstruction only applies to the high order subsystem because we didn't have a very good model of the cross covariance between the low order, like the NGS measurements and the LGS measurements. So that's why we are proposing here this generalized wavefront sensing model. So this is basically for the Schack-Hartmann wavefront sensor subapertures, and this is basically a linear wavefront sensing model, but it's very useful. So going back to the definition of the wavefront slope, so when we get rid of all this noise and nonlinearities, and for this pure, like fully illuminated square subaperture, we know the slope measurement in one direction is basically the average gradient of the wavefront phase in this particular area. And previously, our high order approximation model is basically taking the left side and the right side of the subaperture, and we take the phase difference to approximate this slope measurement. But I mean, this is generally a good approximation, but this has some trouble when considering a natural guide star or like partial illuminated subaperture. So that's why we are introducing this idea of defining a set of grids in the area of a subaperture, or maybe we can define these grids in the area of a pupil to really determine the valid area that is illuminated in every subaperture, and taking all these valid grids or cells or pairs, no matter how you want to call this, into the calculation of the covariance matrix. So this means the covariance between two subapertures will be just calculated from all the valid pairs or valid grid cells in our definition. And this also requires the use of a phase structure function and also the parameters that we identified from the learn step. But the point here is that we can then build a covariance matrix for any wavefront sensor geometries, and this can be used directly in the control scheme. So let's first look at some open loop test results. So this is generated as a comparison between our generalized wavefront sensing model and the numerical covariance matrix. So the numerical case is populated from extremely large number of iterations, and the open loop, noiseless, so geometric identification of wavefront slope. So this is really well converged, and we think this is really close to the real values. So as a comparison, we can see the generalized model is actually working very well, like has shown a very good linearity between the generalized model and the numerical case. The only difference we address here, the red box marked area, which is more clear in the right plot, so which is a covariance value as a function of the subaperture distance. So we know the covariance values really depend on the subaperture distance, but when the distance is very close to zero, so basically the diagonal values of the covariance matrix, or the variance term, which means the covariance between one subaperture and itself. So in these cases, the analytical model might be slightly different from the numerical case, and this is partially due to the resolution of the generalized model. So increasing the number of grids will help a bit, but never fully converge onto this numerical curve. So the residual error is basically from the phase structure function that we are using. But this is not a very big deal because this will be canceled during the tomography process. So regarding the partial illuminated subapertures, this is more relevant to our discussion here, because like say for example, so this is a 5x5 natural guide star configuration, but this doesn't mean anything physically. We are just showing this here for comparison purposes. We can see the subaperture number 10, 13, or 16. They are just partially illuminated due to the center of obstruction, or maybe the circular shape of the telescope pupil. So the covariance value, so what we are showing here in the right plot is basically a diagonal value of the covariance matrix, so basically the zero distance case and the self-variance case. So the covariance value can be quite different from the fully illuminated subapertures. And our conclusion is, given enough number of grades in the generalized model, we can be very, very close to the numerical case. And this is a very good agreement. So we must say that we have done a linear fitting step before doing this plot to get rid of that 1.15 linear factor in the previous slide, as we mentioned earlier. But this is generally a very good approximation. So after this, we can apply the integrated controller based on the cross-covariance matrix we generated from the generalized model. So as a comparison, previously we have to use this split tomography, as you see in the bottom diagram here. So we have to do this dedicated orthogonalization of the high order and the low order modes. So this can be a little bit tricky. There are a lot of discussions here, but we are not going to mention them. What we want to say is now we can use this concise RTC implementation that is only using one loop, simply combine all the least guide star, natural guide star measurements, and we feed them into the predictive reconstructor, and all this pseudo-variable control, all this IR filter, or what we are showing here is actually an exponentially weighted moving average filter, can be directly applied to all these subsystems. So this allows us to have a better performance. So this is an end-to-end simulation result, and this is done by Yao, which is an end-to-end simulation platform, and has already got a decent implement of the split tomography. So we make this comparison here, and this is a full-scale MAVIS system configuration, and we have considered all these electron noises, device noises, and laser spot elongation, and the extended length of the sodium layer. So quite a reasonable comparison between these two methods. And the quick conclusion is we have gained 37.5 nanometer RMS wavefront error averaged over the whole field of view compared to this split tomography case. So this is partially because of the better performance in the low order loop. So as you can see in the right plot, we are showing the residual tip tilt and the plate scale error. And this is definitely doing better because we are doing this predictive reconstruction also for the low order loop. And another part of the gain is from the better estimation of the virtual guide star slope, because we know the virtual guide star has a low order aberration inside, and using this actual low order measurements from the system will help us to better minimize the residual slope. Therefore, we are doing better in terms of this tomography. So another conclusion slide is that we have proposed this model. We have used them in this integrated controller, and we have got a better performance compared to the split tomography, but at a cost of a higher computational load. And this is to be discussed because, like say, further increasing the resolution or the number of grades in our model is not going to help much in terms of the long exposure performance. So the better way will be using this model only to the required subapertures. So for example, the natural guide star subapertures, or maybe the outside subapertures of the least guide star, to achieve a better performance within affordable cost. So our future work will be thus doing this model controller. So all previous discussions are based on a zonal control scheme. So we are going to switch to a model controller, and this will help us to combine the advantages of the split tomography and our predictive controller, integrated controller, so that we can find a way to update only the low order reconstructor when the natural guide star is actually fast moving. So we can really combine the advantages. And also we are planning to close this supervisory loop by taking the realistic temporal evolution of the turbulence into consideration to come up with a better understanding of the update rate of our learning and the applying step respectively. So yeah, that's my presentation. If you have any questions, I'm happy to discuss.
Thanks for that talk, Hal. I'll just wait to see if there's any questions come in. One question I had was on the learn and apply. You have a particular model behind that. Yes. Does that kind of, do you think that would limit the performance of this technique, or?
So I think this learn and apply has been tested on Sky later after the first proposal, like maybe in the next year or like that. but that was more for a MOAO system. So this is like in these MCAO applications, we are only showing this from end-to-end simulations, that this is actually doing a good job. And another good thing is this is a pure slope space reconstruction. So this is very consistent to our GPU accelerated parallelization algorithms. So this is easier for us to, implement in this RTC system.
Right. Okay.
Yeah.
So thanks. I think if there are any other questions, we can take them offline.
Thank you.
So thanks for this talk. So next we have Cedric Heritier talking about Sprint, System Parameters Recurrent INvasive Tracking, a fast and least cost online calibration strategy for adaptive optics.
Hello, can you see the slide?
Yep, I can see your slides.
Same thing as before.
Yep. Perfect.
Thank you, Charlotte. So yes, today we talk a bit about AO calibration, and I will present the Sprint method. I'm currently an engineering and technology research fellow at ESO. And the context of this presentation is the development of large adaptive telescope equipped with prefocal deformable mirrors. We already have a few facilities equipped with such designs, and some bigger and a bit more complex ones are coming up. So in my case, I will focus on the case of the ELT. You can see now a nice image showing the optical propagation to the telescope. And what I'm actually interested in are these two elements: the deformable mirror M4 here, localized on the tower above the M1, and the AO instruments that are located on one of the NASA's platform. So what I'm trying to do is to optimize the interaction matrix of the system. And in particular, I'm trying to fight against misregistration. So these are eventual rotation, shift, or even higher order of optical distortion that could occur during the observation, and that jeopardize the quality and the validity of the interaction. Here I show a small animation showing the effect of misregistration on the performance of the AO system. On the right, you can see a table TSF for an aligned system where everything is stable, at high performance. And on the right, you can see the drop of performance due to misregistration. You can see on the edges some really high frequency patterns. And what's interesting to see here is that this not only has an effect on the performance of the system, but as well on the operation, because misregistration propagates some really high special frequency patterns that require quite a lot of force. So actually, you can see on the image on the left the propagation of the saturation event on the M4 mirror. So here it's a really exaggerated misregistration because for illustration point. So there's a need to monitor and compensate for this misregistration. And I'm currently leading an activity on the topic at ESO here to propose a common calibration strategy for all the first light ELT instruments. So here is the list of all the people that often follow the activity and contribute to the discussion and the reflection. And the current baseline for the first light instrument is to use a pseudosynthetic calibration, where you numerically estimate the interaction matrix from the model, and you just input the correct misregistration parameters. For the estimation of the parameter, the baseline is to use an invasive approach that I call Sprint, and I actually present now. So Sprint stands for System Parameters Recurrent INvasive Tracking. It was presented earlier this year in the paper. The principle is quite easy, simple actually. You have your loop running on your telescope, your AO loop that is in a, let's say, registration state alpha. You acquire a few on-sky measurements, and you inject this into an identification algorithm that is coupled to a synthetic model of the system. And this iterative algorithm basically provides an estimation alpha star of your misregistration that you can actually use either to optically recenter your system or to compute a new reconstructor that is with the correct misregistration. So what I want to talk about today is also about the way to get the on-sky measurement. There's many papers that talk about on-sky calibration already. And the scheme that I consider is to use a modulation of a signal through the AO loop and to demodulate it a posteriori to get a measurement of a given signal for the algorithm. Okay, so let's have a look at how it works with a really normal basic system. It's a simple ELT SCAO system that is representative of what would be the first light instrument. Consider both I and K band, 2 frames delay for my constructor, and what's important is that the misregistration are applied on M4, so everything is static. The M1 pupil is stable, the wavefront sensor is stable, and M4 eventually moves, and that's why I simulate misregistration. And the type of invasive signal, so on-sky measurement that I get, is to use one single KL mode of the model basis. This result of a trade-off for versus accuracy versus force request. And if you want more detail about this, I have some extra slide that I can show you. So let's have a look at an example of application. We have a misregistered system. Here you can see the typical values that you can get, so quite realistic, I would say. And I have a system operating in K band, and I apply a sinusoidal modulation at 90 Hertz of the KL mode I just showed you earlier. Here, what you can see on the left is a low flux, and on the right, a high flux application of the method. So you close the loop, you see that you have misregistration because you can see some pattern on the sides. And you can see that I'm currently doing a modulation with a high amplitude for the low flux and the lower amplitude for the high flux. You can see the ring of the KL mode here. And after this modulation of the signal, you have the estimation of the parameters, the realignment. And once you realign everything, you get back to an optimal operation regime. So this is an illustration of the way Sprint actually works. You can see it's quite fast actually. And what I really want to discuss today is how to get the on-sky measurement properly. The first question is to go either closed loop or open loop modulation of the signal. So if you go open loop, it's actually quite easy. You just modulate the mode on the mirror and you look at the wavefront sensor signal afterwards. This has the impact on the linearity of the sensor. You might be impacted by the linearity of the pyramid, but you have the benefit of being completely free from the loop projection. Since we have to work with a pyramid, actually, you have to apply a closed loop modulation of your signal. So in that case, you have to apply the modulation above the closed loop command. And this allows you to operate the pyramid in its linear regime. But this has a cost because you are impacted by the loop projection. And how is that important? Here I show an illustration of what's happening when you actually apply a closed loop modulation on the system. You can see here I apply a KL mode, and you can see that it follows the sine wave that I'm representing at the bottom. And this is the OPD seen by the wavefront sensor. So it goes from minus to positive, everything as we expect it to be. But in that case, there is no misregistration. However, if you go to a system that is actually impacted by some either rotation or shift, what we witness is that the OPD seen by the system is affected by some kind of dynamical behavior. So you can see kind of a rotation of the mode and kind of a shift of the mode as if you were swapping through your images on the smartphone. And this is really visible when you change the sign of the mode. And what's actually interesting to see is that if you operate the same thing in open loop, so open loop with this registration, you don't see this dynamical effect. And so this actually is quite important. And to understand the origin of the effect, you have to go back to how your loop is actually operating. When the system is aligned, you actually have the product between your constructor and the interaction matrix that is more or less the identity. So you have this orthogonality that is ensured, and that makes that if you input a given mode, KL mode, you reconstruct this mode and only this. However, if you move to a misregistered system, this is not longer true because you only update the interaction matrix of the system. I mean, it's not updated, but it moves from d alpha 0 to a d alpha star that is different. And you lose this important property of orthogonality. So that means that when you actually apply a mode, you will actually be coupled with other modes. And this is what is illustrated here for typical misregistration. You create some couplings between the modes. And this has an important effect because you actually modulate modes, but other modes at the same time. So it makes it really hard to disentangle it when you do the demodulation process. And so now the question is, how does this actually affect the estimation of the parameter? Here I show the shift estimation error versus the modulation frequency. So you swap a large bandwidth of modulation frequency. And what you can see is that, as expected, when there's no shift on the system, there's no error in the estimation. So whatever modulation frequency you apply, you get the correct estimation of the parameter. However, we can see that the estimation of the parameter is really dependent on the modulation frequency. And what's interesting is that there's one point that seems to be the best working point. It seems to say, okay, you should always operate the modulation at this modulation frequency. So when you see this, it's interesting because it reminds a bit of the rejection transfer function of the system. So what's come to mind is to say, well, this should only depend on the rejection transfer function. So you have an underestimation of the parameter and then an overshoot here. But you have to be careful because since we have couplings between modes, you actually have lost this hypothesis of independent controller. So it's a bit more complex and you have to consider a rejection transfer matrix. So what does it mean? It does depend on the loop rejection. So it depends on the loop delay, it depends on the gain, it depends on the controller you use, but essentially it also depends on the variation of the pyramid optical gain, which means that it will depend as well on the sync variation. And as you could see here, it depends also on the couplings will also depend on the misregistration that you have on your system. So just to give a quick example, here I have done the same work with an I-band sensing system. So you are impacted with much stronger optical gains. And you can see that there is when you don't do any optical gain compensation, you have a different best working point. That is a function of that depends on the scene of your system. So this is important to keep in mind. And when you actually go for optical gain compensation, you can see that all the curves kind of align around the same best working point. So it shows that you really have to be careful about how to compensate the optical gain if you want to do a proper measurement. So take-home messages. If you operate closed-loop modulation, choose your modulation frequency wisely. Know your gains. That's also maybe easy to say, not harder to do. And what I want to also say is that the same effect has been identified if you do a push-pull measurement. So a realistic push-pull measurement, it's not only with the sine wave, but there's maybe two things to mitigate a bit this effect, is that since you have a non-sky measurement of the KL mode, let's say you actually have a feedback on the effective gain on this mode, so you can know more or less where you are with respect to this. And as well, since the estimation is iterative, you have a bit of a margin on the estimation of the parameter, so you might converge a bit slower than you want, but you will converge. And as a conclusion, so I presented quickly Sprint, a fast and robust method to extract the misregistration. I showed that the perturbative signal can be really, really small and negligible, but provides really high accuracy estimation. And there's many flavors to implement the method for bootstrap, online operation, and so on. But if in terms of on-sky measurements, if you can go open loop, go ahead. If you have to go closed loop, go ahead, but watch out for your loop rejection. So that's all from me. I don't know if you have a question.
Thanks, Cedric. That was a very good illustration of a complicated measurement process. I guess one question I had is if will this, or if you had some, would this also impact your kind of optical gain measurement if you're using modulations to do some optical gain measurements?
So actually, I think what could impact the optical gains would be the misregistration, because you don't have the same residual of turbulence. So you might have a small effect of misregistration on the measurement of the optical gains. However, I did not notice any dependency, I mean, really small variation on the optical gain estimation as a function of the modulation frequency. So it seems to be quite flat, I would say.
Okay. And we have a question from Glenn. Are you synchronizing your detection correlating with DM commands or injected modulation?
Okay, I'm reading the question as well. Actually, yeah, I mean, I'm trying to, I'm not sure to understand the question here. But yes, basically what I'm doing is that I'm applying the perturbation over the closed loop command, and then basically, yeah, doing a local detection after all. So you know which modulation you apply, and so you know which modulation you should look at to demodulate. And yeah, maybe I can have more information on the question. I'm not so sure about the question here on the Discord channel.
Okay, yeah, Glenn, maybe you can elaborate on your question on Discord. Okay, and apparently, he couldn't hear your answer. Okay, yeah, if we switch to Discord for that conversation. Okay, thanks, Cedric.
Okay, so wait, if you can stop sharing.
So now we have Arseny Kuznetsov talking about extending the limit magnitude for lift for GALACSI NFM.
Okay, hello everyone. Can you hear me?
We can hear you. I can't see your slides.
You can't. Resume share. Okay, you should see now.
Yes, we can see them.
In a proper mode.
Yes, we can see the.
All right.
Great. Go ahead.
So, hello everyone. Excited to be here today and present the topic. My name is Arseny Kuznetsov, and I'm a first-year PhD student at ESO, ONIRA, and LAM. And presented today the topic extending the limit in magnitude with lift for GALACSI narrow field mode. So I was doing this project for my master thesis, and I also want to use the chance and say thanks to all the people you see here who made this topic possible. So first, I will not spend much time on introducing the general context of a GALACSI narrow field mode. What is important here that GALACSI narrow field has a low order wavefront sensor called IRLOS, you can see it here, which is essentially a Schack-Hartmann 2x2, which can sense defocus, deep tilt, and true astigmatism. And recently there was a proposition to go for so-called field pupil mode, when you basically remove these 2x2 subapertures and just employ the whole field to reach the ultimate sensitivity of IRLOS. The problem is here, of course, that you lose ability to control defocus or astigmatism in this case. And actually you should, because, for example, we can't have a drift of the sodium layer, which will be seen as a defocus. So we need to do something with this. And that's where the lift comes handy. So basically, lift stands for linearized focal plane technique. And idea behind this is fairly simple. It's a phase diversity algorithm, which employs the single frame. And it's based on introducing the known amount of astigmatic diversity into the optical path. This astigmatism allows you to resolve the ambiguity of sign for even modes and including defocus. So basically, and moreover, it's very easy to implement in our case in IRLOS because we just need to insert a astigmatic lens into the optical path. And so our baseline to be able to sense a defocus or even high orders with the lift. And what's important to do it in a low flux. And fortunately, lift is pretty much suited for this task because we can see here that inside the lift estimation, we have this regularization term, which is basically the weighting by the noise statistics. And it helps us, for example, in a high flux regime, lift focuses on the whole image, as you can see, to extract information from. In a low flux, lift tends to concentrate its efforts near the PSF core, neglecting the noisy background around, which can be handy in low flux regimes. And so we introduced lift. Now we have a question. So basically to answer. For first, how big the aberrations, amplitude of aberration we can sense with this lift, and which kind of astigmatic diversity we should introduce. how faint we can go, the limiting magnitude for the NGS we can employ with lift, how much modes we should reconstruct, and of course, how will it perform in realistic conditions. To answer the first question, we can look at this plot. It's fairly simple. So it's basically synthetical simulations where we introduce the single SR-Nicky mode and try to reconstruct that with lift. And you can see result for the two different diversities introduced. You immediately see two things. First of all, the linearity range of lift makes it not possible to operate an open loop, so it's suited for the closed loop. Second, more diversity you introduce, basically the higher linearity range you can have on reconstructing several modes. At the same time, you should be careful with flux because you're basically spreading your PSF and dimming your PSF. And also you can see that if we reconstruct the mode which we use as a diversity, we have a shifted 0 point. So probably it's not the best idea to reconstruct it. Probably we should remove this mode from reconstruction and see what happens. Oh, well, yeah, we have even more linearity range on some modes if we like reduce the number of constructed modes. But here we should be careful because now we cannot describe the shape of the PSL well enough, and we will cover this later. So here is the message that, yeah, probably the number of modes we should reconstruct really depends on the case we're working with. And so that was a pretty much easy simulations. What if we go on the serious ones? So basically here on this plot, you can see the sensitivity scans. What does it mean? So on y-axis, you have a difference of a reconstructed and introduced OPD. Of course, it's a simulation, so we control it perfectly. We also have information of how much of absolute value of the RMS of the aberrations we will introduce into the synthetic PSFs. And so basically we will introducing aberrations, then introducing it for a different flux level and scanning over the range of a different flux levels and try to reconstruct. As here we can see that probably that's not very optimistic. If we try to reconstruct 9 modes and we employ pretty much realistic conditions for those PSFs, because those aberrations mimicking what we will see further on sky, they're also polychromatic, they incorporate some residuals. And well, we see the sudden drop of the accuracy around the magnitude of 16, 15. So it's not so good. What can we do with this? First, of course, we can increase the exposure time, or we can try reconstructing less modes, and we have an immediate increase in accuracy. But it's in a low flux. If you look in a high flux, we can see here that in this case, we have lower accuracy than before, because of course, as I said before, we can describe the shape of PSF less accurately. And here we have a plateau mostly because of the residuals. And so with basically aliasing we see here. And here is the fact, yeah, again, aliasing because we just throw away our other modes, except for example, tip tilt and defocus. And well, it looks pessimistic. Is it so bad for lift? So it's time to look in the experimental verification. That's what we've done in the lab first, with the setup you see here, which basically mimicking real ear loss and using the same detector as we have now on VOT. So so it's similar to linearity range scans for defocus. So we were just moving the whole stage relative to detector to achieve the known amount of defocus and try to reconstruct it with lift. And for the high flux, experimentally, we have pretty decent results, as you can see. But we also tried for the low flux. And we can see here, actually, that we were able to reconstruct ridiculously faint magnitudes. And well, that's pretty optimistic. And especially around 0. And well, that's good. But it's worth saying that actually those experimental conditions, they're pretty soft because we were not introducing anything else but defocus. And yes, everything was well controlled in the lab, and also PSF spectrum was more or less known. So in case we need to verify it on sky in any case to have the grasp realistic understanding of what we should expect. That's what we done as well. But on sky, we have another concern. For example, we should know some parameters of the system, like calibrate them before. We don't know them actually precisely. We have ADC residuals, and we also don't know exactly the shape of NGS, because NGS can be not just star, it can be extended object. And this is very important for the lift estimation, because lift should know this. And so basically, this is some of the results we had on sky. Again, methodology is pretty similar to the experimental verification before. So we just, on VOT, we just introduced a different known amount of defocus by just moving the focusing stage and try to reconstruct it with lift. All on sky's results you will see are in a high flux. Here you can see that defocus is more or less reconstructed by the lift. And moreover, we try to reconstruct the higher modes you can see here. And so basically what you can see, okay, the focus is changing as expected, but as well, we have a pretty stable behavior of higher orders here. And it gives idea, probably we can reconstruct and calibrate NCPAs using lift on ear loss, but well, it's appeared that not really, because when we moved and did another defocus scans, again, we have a different stable behavior of higher orders, but as you see here, the set of aberration is different. So amounts of aberrations is different. What else is different is the assumption for the object. So you see here, it's like assumed to be Gaussian of 2 pixels. Here is 1.25 pixels. And if we don't do this assumption, so basically the reconstruction fails completely. So it's very important, and it's still an open question how to do it on sky. Should we calibrate the shape of the object before, just without the lift lens? And or we should jointly estimate the shape of the object and aberration, somehow introducing additional degrees of freedom. So it's a still open question. And there are a few more scans we performed. Those one actually were performed here a week and a half ago on VOT again. And again, we have a more or less a decent reconstruction accuracy for defocus and more or less stable operation, reconstruction of the higher orders. This one is a bit fuzzy because we were just randomly sampling the focus range and measuring, like introducing the focus here, here, here. And so that's why actually this is this kind of subtle shape. And yes, in the bottom, you can see actually the real PSF, which we captured and reconstructed one. So just to finishing all of this, in the conclusion, what we want to say, yes, we prove that lift is capable to reconstruct defocus on VOT, capable of operate on ear loss. The problem is that with all those realistic contributors to the PSF quality, it's still hard to achieve stable estimation in realistic case. Regarding the low flux, lab experiments showed that lift can efficiently reconstruct the focus even on the low flux. But again, lab experiments were pretty soft. And on simulation, we see the different picture that actually on low flux, there are some problems, but probably simulations are just too harsh. So basically one of the future points is to verify it on sky in a low flux. And also what we want to do, because it was shown actually on presentations of this workshop before, that lift is capable of detecting low wind effect in some sense. It was already done on simulations, and yes, it is, but it's just not presented in this presentation due to lack of time. So probably in future, in a very next close future, we will try to recreate low wind effect on DSM and try to sense it by lift. And just to general conclusions that currently I'm proceeding with a PhD on the topic of self-learning AO, and we'll also try to extract information from PSFs as I did with lift within the scope of my PhD. So I hope it will be an exciting time, and yeah, stay tuned. I think that's it from my side, and thank you for your attention.
Great, thank you, Asmi. Do we have any questions? Just wait a second. Do you have a kind of proposal for what sort of self-learning you wanted to apply to lift?
Well, not to lift in general, it goes beyond the lift. Right. With self-learning, well, just basically, yes, it's a bit straying away from the topic of lift. So we want to kind of couple some linear models, for example, used for PSF predictions with some machine learning based techniques, and try to probably absorb some non-linearities or some factors which are not included in this linear models into this machine learning part. And so basically, it also was mentioned in I think first presentation yesterday. That's like just briefly what we want to do in terms of this self-learning. But it is just some point about the general scope within what I'm working in. It's not only about lift.
Yeah. Okay. So thank you for your talk.
Thank you for your attention.
And so next we have the last talk of the session. So Vincent Champollion, and talking about a comprehensive model for noise propagation through Fourier-filtering wavefront sensing. So go ahead, Vincent.
Okay, can you hear me?
Yes, we can hear you.
Okay. So hi everyone, I'm a third year PhD student at LAM and Onera. And so I'm going to give a talk which is much more conceptual, let's say. So it's not really fitting with this session, but there were a switch with Carlos' talk, that's why. So I want to give a talk about a comprehensive model for noise propagation through Fourier-filtering wavefront sensing. So it's kind of stepping back a little and trying to come back to some fundamental stuff. So it's, of course, if you listen to Olivier Guillon yesterday, there are strong links between this talk and the one that, it was a nice introduction, Olivier, your talk, so thanks. So my outline of my talk, it will be in two parts. The first part is to introduce to you this noise propagation model that will be a way to revisit the fundamental limits of noise propagation in a Fourier-filtering wavefront sensor. And the second part will be to try to use this model to kind of build a new comparison of the famous Fourier-filtering wavefront sensor, which are the pyramid and the Zernick wavefront sensor. So for the noise propagation model, I will try to just give an idea of how we derive it without going into too much details. But the first thing about this is the fact that the way we proceed the Fourier filtering signal is the full frame approach, let's say. So we call this reduced intensities, where the signal that we get is the signal on the camera minus the signal which corresponds to a flat wavefront, the reference intensities. So here it's an example given for the four-sided pyramid. Okay, so this is the way we proceed for all the masks, the signal. So actually, to derive this model, what we use is this kind of formula where we propagate the noise into the reconstructor. So this formula was already really used by Rigaud and Gendron to derive the famous noise propagation model for Schack-Hartmann. And so we exactly use the same for the Fourier filtering wavefront sensor, actually. So just the first thing is how do we compute this noise propagation, the covariance, the noise covariance matrix. So you know that for there are two kinds of noises that are affecting our measurement. The first one is the redot noise, which we are going to assume uniform on the detector. So this one depends only on the detector, so it doesn't depend on the mask, neither the modulation of the Fourier filtering wavefront sensor. And the other kind is the photon noise, and this one is non-uniform on the detector. It depends on the illumination on it, and so it does depend on the mask and the modulation. So actually, when we can plug this in this formula, and we can extract the diagonal term of the error covariance matrix to find back our noise propagation model. And so this is it. This is the formula we found. So actually here, this is the mode that we are looking at, and the parameters of the system. So the number of photons for the measurement. This is the number of sampling points in the pupil. So it's in two terms, of course. The first one is the redot noise term, and the second one is the photon noise term. So now I didn't speak about the two most important terms, which are these ones, which are depending on the sensor we are using. So this is what we call the sensitivity. So on the left, this is on the left, this is the sensitivity to redot noise, and on the right, this is the sensitivity to photon noise. So they don't need to be the same. And so we call this sensitivity. So the higher are this term, and the lower is the noise propagation. Okay, so now how do we compute this term? That's the most important part. So when we derive this formula, we have a way to find it, actually. For example, for a given mode, how do we compute the sensitivity? So for the redot noise, what we do is we extract the column of the interaction matrix corresponding to this mode, and we just do the RMS norm of this map. Okay, I remind you that we are working in full frame. And how do we do for the photon noise? So this is okay, maybe more new. How do we do? We just extract also the map of the interaction matrix, and we divide it by the square root of the reference intensities, term by term, and then we take the RMS norm. Okay, so this is a term by term division. And so these two kind of sensitivity, actually, we can show that they are lying between 0 and 2. They are bounded. This can be shown by the Kramer-Rao bound and the Fisher information. So there are some references. So yeah, that's the cool thing about this criteria. we know what are the maximum sensitivity for these two kind of noise that we can reach. It's the ultimate sensitivity we can have. So in this propagation model, the ideal sensor in terms of sensitivity will have, okay, this number, this term will be equals to 4 and the other one also. Okay, so this is this noise propagation model. So now we can try to test these two kind of sensitivity on the famous wavefront sensor. So first I will speak about the pyramid class. And so what we can do with the pyramid class, you may know that it's quite studied a lot. Does the number of faces change something in terms of sensitivity? So let's try to apply our criteria to see what's the difference. So the first thing is about the redundant noise. So this is are quite actually already well-known results. Is the fact that here I put the sensitivity with respect to the spatial frequency for 3 different modulation radius. So actually, you see that the thing that you can see is that there is an order, and so the more faces you have, and the less sensitive you are. When you are modulating, you can see that there are this famous drop in sensitivity for the spatial frequency which are lying into the modulation radius. So okay, nothing really new here. The more faces you have, the more pixels you're using, so you're less sensitive, and that's a big argument for people who are trying to test the three-sided pyramid actually. Okay, so this is okay. So you can see that we are lying, but now on this figure, we know what is the maximum sensitivity. It's 2. So we see that here we are kind of quite far with the pyramid class. Okay. Then for photon noise. So what's happening for photon noise when you compute with our definition of the sensitivity for photon noise without modulation? Actually, all the masks are equals. So the number of faces doesn't change the sensitivity to photon noise. But when you're starting to modulate, actually you find back a kind of order between the pyramid, and the less faces you have, and the better it is when you're modulating. And also what you can see, so okay, so no modulation, same sensitivity. And when you're modulation, the number of faces makes a difference. And also, there is an important loss on all the frequencies, okay? Because when you modulate, some photons are not, let's say, involved in the sensing anymore. So it's more just photon noise. And so that's why when you're modulating, there is a drop in sensitivity, which is quite high, actually, between no modulation and modulation. Okay, so that was for the pyramid. So for the pyramid class, we tried this criteria on the bench. So by building interaction matrix on different kind of pyramid. So we use the loops bench for that. So it's a bench where we can emulate any kind of phase mask with a SLM. So we emulate a lot of different pyramid. And we can find back this kind of result with the photon noise, for example. When you're not modulating, they are almost all equals. And when you're modulating, you have this order, this sensitivity, which depends on the number of faces. Okay, so that was for the pyramid. Now we can focus on another kind of mask, which are the Zernike class, the famous Zernike class, known for its really high sensitivity. So I remind you that this class has 2 parameters, the mask of the Zernike wavefront sensor. There is the diameter and the phase shift, okay? So usually how it's used, the phase shift is a P/2. So this is the phase shift to create a constructive interference to map the phase. And the diameter is chosen this way, it's 1.06 lambda over d for classical Zernike. So actually, what we are going to try here is to test our criteria for different diameter of the dot, of the Zernike dot. We are keeping the P/2 shift because it's optimal actually. And so when you increase the diameter of the dot, you see that you are changing the reference intensity. So here are for 3 kinds. So the classical Zernike, the Zernike with a 2 lambda over d diameter, and for 5 lambda over d diameter. Okay, so actually when we do that and we compute the sensitivity for readout noise, we see that there is quite a big difference actually. We see that the classical Zernike that we use usually, this one, is lying here. And actually by increasing the diameter, we can jump to much higher sensitivity. There's almost a factor 2. And so the Zernike wavefront sensor sensitivity can be optimized actually, and we published a paper on that. But you have to spot that all the frequency which are lying into the dot are not seen anymore. That's why, for example, for this large dot diameter, 5 lambda over d, all the frequency which are inside the dot the sensitivity is lost. So that's a trade-off that we have to do between low and high frequencies. But still, we are gaining a lot for all the other frequencies. And for photon noise, actually, that's the same. we improve also the photon noise when we increase the dot diameter. Okay, so actually, if we plot on this the non-modulated four-sided pyramid, for example, here will be below the Zernike, the classical Zernike, but actually, when we apply this criteria, we see that the non-modulated four-sided pyramid is more sensitive to photon noise than the Zernike wavefront sensor as it is used with the 1.06 lambda over d diameter dot. Okay, so that could be surprising actually, this result, but that's perfectly normal because if we think about the classical Zernike wavefront sensor with this dot diameter, if you look at the reference intensities, the useful pixel for the sensing, the linear pixels are inside the pupil, and actually half of the photons are outside of this pupil. So there is a lot of unused photons when we are using the Zernike wavefront sensor with a small dot. Okay, that was all for the Zernike wavefront sensor. So we did also on the bench because okay, we can emulate also Zernike wavefront sensor. We validated these results also, so you can see here for KL modes also with the you can see that we are losing the sensitivity for lower order modes, but we are really improving for higher order modes. Okay, always this trade-off between the two, I mean, low order and higher order frequencies. Okay, so I can jump to my conclusion, which will be a little long, but that's okay. So the noise model with we established a noise model with two kinds of sensitivity, of course. So the two kinds of noises, two kinds of sensitivity, readout noise and photon noise. And the photon noise is actually a really important metric to compare Fourier-filtering wavefront sensor, but you all knew about that before. But here we show that, okay, in our criteria, the sensitivity, we have an upper limit for the sensitivity. Okay, and so, of course, I have to speak about the Olivier Guyon paper, who is already deriving a photon noise criteria for his sensor. Okay, here the argument is that our derivation is really easy, actually. I mean, that's really simple to derive. And also, it's not analytical. So, I mean, the way we compute the thing at the end is that we take the interaction matrix. And once you have the interaction matrix of your sensor, you can build your sensitivity for this sensor. So it works for all kinds of mask and modulation. And it's more accurate also because it's taking into account, for example, the behavior for lower frequencies and stuff like this. And so, for example, okay, in Olivier's paper, for example, the Zernike will lie in the best thing you can do, so the two limits. But actually, we see that to reach this limit, we have to kind of have a trade-off, and we need to put more light into the dot spot. I mean, the Zernike dot. So there is kind of a trade-off to have. So it's not so easy to reach the two for all the spatial frequency, actually. Okay, so that was kind of the thing about this. And maybe to do some perspective, I think I have maybe 1 minute left. Okay, so now that we have this criteria, actually we can go beyond the Zernike wavefront sensor optimality, which are really already really close from to the Zernike wavefront sensor. But you have to have this trade-off between low and high frequency. And actually, we built a new class of sensors that will be presented soon, where we can try we found a way to try to gain on this low frequency and to kind of break the trade-off between the high and low frequency sensitivity. And another thing I wanted to say before finishing is that this study was, of course, done in a linear regime. And so, of course, if we take the optical gain in account, actually, it's really important because it's going to change the sensitivity. And Olivier really said that yesterday. There is a kind of, I call it the effective sensitivity, actually. So the sensitivity is a loss when you have like residual phases. And so maybe, I mean, that's an idea. We should define this kind of sensitivity where it's something like the optical gains times the sensitivity that I described here. So we have to take into account that to have this really effective sensitivity. So yeah, it's really what Olivier said yesterday, the part of his talk. So that's all for me. I hope I fit in the time.
No, that's great. Thanks.
Okay.
There's a few questions in the Q&A. So one from Andreas. How come the noise terms do not depend on the chosen control matrix or interaction matrix?
So how cannot, sorry, can you repeat the?
How come the noise terms don't depend on the chosen control matrix?
No, it depends. It depends. Sorry, maybe I was not clear. Of course, it depends. So actually, maybe I can come back to the. So it depends. Actually, the way I compute the sensitivity. Oh, sorry. So the noise term do not depend. So the noise term depends also on the structure of the sensor, right? Because here you see that, I mean, the photon noise term depends on the Fourier-filtering wavefront sensor we are using, because it depends on the illumination pattern. So maybe I don't know if it's because, I mean, I'm not sure if that was the question. Yeah, okay. So
yeah.
maybe, okay, maybe the other thing, yeah, is the fact that we are in a linear regime, so we can assume that this map, actually, I mean, the reference intensities are the signal on the detector, because we have really small phases. So we are, let's say that our signal on the camera is really close from the reference intensities. Maybe that's the thing, the question, I guess.
Sure. I mean, yeah, you maybe you can take it offline onto Discord. Okay, thanks for that interesting talk. And so we're at the end of the session. Ran a little bit over, but I think we'll still be back at 12 Chilean time